So, should you, please.
Okay, good morning, everyone. So I'm very sorry for the mistake. Okay, so I'm very happy to give the report today. The name of our report is the Parametric Fokker Planck equation. So it's a work done by Wuchen, me, Hongyuan, and Haomin. So I decided to separate the report into 5 parts. So first, I will briefly introduce the backgrounds of Fokker Planck equation. And then I will briefly say something about our motivation. And in the third section, I will say something about the details of the derivation, and then show you some algorithms and results, and finally say something about our ongoing research and future directions. Okay, so first is some backgrounds of Fokker Planck equation. So Fokker Planck equation is a very important equation used in physics and statistics and also geometry. And recently it has also drawn the interest of machine learning community. So this is the conventional form of linear Fokker Planck equation. So you can see it's an evolutional equation, evolutional parabolic equation. It actually describes the evolution of the probability density, rho xt. And we will just call this function v the potential, and we call that beta. We assume beta is non-negative and call it the diffusion coefficient. And here is the most famous interpretation of Fokker Planck equation. So you first consider a stochastic differential equation, also known as the Ito process. Here this Bt is the standard Brownian motion. So it describes the particles, the motion of particles inside a potential field under the affection of white noise. And if you fix the time t and you consider the random variable xt, we denote rho xt as the distribution of the xt, then you can show that rho xt satisfies the Fokker Planck equation. So it describes the Fokker Planck equation describes the evolution, distribution evolution of SDE. But actually, our approach will use another perspective of Fokker Planck equation. That is, Fokker Planck equation can be treated as a Wasserstein gradient flow of relative entropy functional. So Alex has already introduced something about Wasserstein manifold. So I will go quicker. So the Wasserstein manifold is composed by probability distributions rho with finite second order momentum. And you can verify that the tangent space at a rho is composed by the functions whose integral equal to 0. Okay, and once we have this manifold P, we can define a distance function, which is called Wasserstein 2 distance on it. And it is defined like in this way. And the interesting thing is that such distance can induce a metric on the tangent bundle of P. So we call the metric tensor GW. And here's the definition of the tangent bundle metric tensor GW. So it was first given by Otto in 2001. So the definition is like this. So you fix a rho on P, and you consider any 2 vectors in the tangent space. Then the definition is GW rho 1 dot rho 2 dot is defined like this integral. Such psi 1 and psi 2 are solved from these 2 elliptic equations. And actually, you can show that under some mute conditions, this metric tensor GW is actually positive definite. And so this makes P together with GW a Riemannian manifold. And later, we will just call this manifold Wasserstein manifold because we are using the Wasserstein metric. Okay, and once we have the Wasserstein manifold, we can compute, given a smooth functional f, we can compute the Wasserstein gradient. Actually, it is the manifold gradient of this functional f. So if you are familiar with the differential geometry, you know the manifold gradient equals to the inverse of the metric tensor times the flat gradient. So in this case, it equals to the inverse of the Wasserstein metric times the flat gradient, which is the L2 variation of f. And you can verify that the inverse of Wasserstein metric tensor is this differential operator, negative divergence rho gradient. So here's the formula for Wasserstein gradient. And once you know how to compute Wasserstein gradient, you can formulate the Wasserstein gradient flow. And here's the formula. It's actually already a evolutional equation of rho. And how to relate this with Fokker Planck equation? You only need to consider a special functional, which is called relative entropy. So it looks like this. So it is also KL divergence. So it has different names: KL divergence, relative entropy, or even free energy. So they all represent the same thing. And if you simplify this, you get this. So I will just simply drop that constant later. So we just consider the first two terms. And we plug this f into here. And you carry out all the computations. You will find what you get is exactly the Fokker Planck equation. So this is why Fokker Planck equation can be treated as the Wasserstein gradient flow of relative entropy. OK, so these are the main backgrounds we are going to use in our project. And here, let me introduce some motivation of our research. So the main motivation, there are 2 points. So the first point is that we are actually, the evolutional equation, Fokker Planck equation, can be treated as an infinite dimensional ODE. And if we project this infinite dimensional ODE to the parameter space to get a evolution dynamic in parameter space, it is actually a finite dimensional ODE. So we are actually transforming an infinite dimensional ODE to a finite dimensional ODE, thus reducing the computational complexity. And another motivation is that by doing so, we are achieving efficient sampling method to generate samples from SDE. So this is very different from the MC method or the momentum method. Okay, so now let me say something about our derivations. So we are actually inspired by the Wasserstein information geometry introduced by Li and Montouffin last year. So this is actually a combination of Wasserstein geometry theory and the information theory. So our treatment is actually can be divided into 3 steps. First, introduce a parametric distribution family, and then pull back the Wasserstein metric tensor onto the parameter space. And last, compute the Wasserstein gradient flow on the parameter space. Okay, let's do it one by one. So first, how to introduce a parametric family. So we are actually inspired by some research in deep learning. Especially the generative adversarial networks. So actually, they use parametric push-forward maps to approximate very complicated distributions in very high-dimensional space. So since the push-forward maps shows their strong ability, that is why we choose push-forward maps to parameterize our probability distributions. So here's a simple definition of push-forward maps. And our idea is to parameterize the push-forward map T theta, and we use T theta to push forward a reference measure P to get the parametric family. So we will call the parametric family P theta, and we call every element in this family rho theta. Okay, and to fit every rho theta into the Wasserstein manifold, we assume it to have the finite second-order momentum. And also, we assume it is inevitable and invertible and smooth. So there are many ways to choose T theta. For example, you can choose it as a affine map. You can also choose it as a linear combination of basis functions. You can definitely choose it as some neural networks. Okay, that is how we introduce the parametric family. And then I will say something how to pull back the Wasserstein metric onto the parameter space. So we are going to use the well-known operation pullback in the manifold theory. So here's our situation. We have the parameter space. We use push-forward map to map a theta to rho theta, which is an element in the Wasserstein manifold. So we already have a metric GW on the Wasserstein manifold. We want to use this map to pull back GW onto theta. That is exactly what we want to compute. We call the pull back the metric capital G. So if you assume that our parameter space is an open set in Rm, you can show that g theta is actually a bilinear form on the tangent space, which is also Rm. And thus, g theta is actually a m by m positive definite matrix. And the following theorem shows that how do you compute g theta exactly. This is the formula for g theta. So the main ingredients is this psi function. So this psi is composed by m small functions, and each psi k satisfies this elliptic equation. So this equation is actually very important in Wasserstein geometry. Sometimes it's called the Hodge projection or Hodge decomposition. So you are actually projecting this vector field, partial theta kt theta, onto the gradient field. So it's a kind of projection. And later, if I still have time, I will come back to this equation when I say something about our algorithm. Okay, and you know this equation doesn't have explicit solution when dimension is larger than 1, but when dimension equals to 1, you can directly integrate this equation, and you will get an explicit solution for the metric tensor g theta. And we also have a theorem that guarantees the positive definiteness of g theta. So I will just skip this one. And now let's come to the parametric Fokker Planck equation. So as you know, the original Fokker Planck equation is the Wasserstein gradient flow of relative entropy on Wasserstein manifold. So to do the similar thing, we just compute the relative Wasserstein gradient flow of the relative entropy on parameter space. So we can introduce the relative entropy on parameter space as f theta equal to relative entropy of rho theta. And you just do the gradient flow on parameter space, and you get this ODE. So we will call this ODE the parametric Fokker Planck equation. Okay, and here's a natural theorem from submanifold geometry. So if you assume theta t is the solution of the parametric Fokker Planck equation, then you can show that the rho theta t is actually the gradient flow of relative entropy on the submanifold. So there is a submanifold relation here. And as you know, the gradient of a function on the submanifold is actually the orthogonal projection of the exact gradient onto the tangent space of a submanifold. So there's an orthogonal projection relationship here, and it is actually quite useful when we want to establish error analysis. Okay, and as we know, the parametric Fokker Planck equation can provide an approximate solution to the original equation, but there are some very special cases that parametric Fokker Planck equation really solves the original equation. And here is the case. So we consider the initial condition is Gaussian, and we consider the potential here V is a quadratic potential, and we assume T theta is a affine map, and the reference is standard Gaussian. Then under this case, if you solve the parametric Fokker Planck equation, assume the solution is theta t, then rho theta t is the exact solution of this equation. And the proof is actually in this lemma. So I won't read it, but I will give an intuitive explanation of it. So the lemma just says that you consider this vector field. If it is the linear combination of these vector fields, which comes from the derivative of t theta, then this exactly means that this equation holds. Then you can show that the submanifold gradient is the exact manifold gradient. So in this case, there's no local error. So why this is true? Actually, it means that this gradient flow, this vector function is actually the vector field that moves the particles in the real Fokker Planck equation, and this partial theta t theta zeta is our artificial vector fields that moves the particles in our parametric Fokker Planck equation. So if they agree with each other, there's no local error. And for our case, so in this quadratic special case, you can show that this equation is always true. So there's no local error at any time. So that means our Fokker Planck equation gives the exact solution of the original equation. Okay, and there's an interesting corollary. Since we know rho t equals to this one is the exact solution, since P is the standard Gaussian, T theta T is an affine map. So affine map push forward a Gaussian still gives you a Gaussian. So that means the exact solution of this Fokker Planck is always Gaussian. So this is already known result in Fokker Planck equations. We just reprove it under this framework. Okay. Now I can say something about our algorithm and show you some results. And we actually tried two T theta. The first T theta is the linear combination of basis functions. And when dimension equal to 1, it is very easy to compute. The metric tensor G is very easy to compute. It's just the expectation of phi I, phi j. You can use a Monte Carlo to approximate G. You can also use Monte Carlo to compute gradient theta f theta. And thus, you can apply forward Euler to solve the parametric equation. And here are the some results, numerical results. You consider this potential function Vx equal to that form. So you can imagine that it has two local minimizers at -1 and 1. And we consider beta equal to 0 and 1/4. So the first line shows the numerical results when beta equal to 0. So we just, at different time node, we sample points from rho theta t, and we make histograms. So these are histograms at different time. So when beta equal to 0, there's no diffusion. So you can imagine all the points will converging to the -1 and 1, the local minimizers. So this is captured by the results here. And when there are some diffusion, beta equals to 1/4, you can see you can show that. So the classical theorem says that the distribution will finally converge to the Gibbs distribution, which looks like this. And this is also shown in our numerical results. So these are the 1D case, and we also have some higher dimensional case. So for higher dimensional case, we try T theta as normalizing flows, which is a special kind of neural network. It was introduced by Razan and Mohammed in 2015. So the form looks like this. So there are mainly two technical advantages why we choose normalizing flow. First, it has shown strong ability to approximate complicated distributions in high dimensional space. And another advantage is that the relative entropy f theta has an explicit and concise form. And that will be very easy to compute on the deep learning framework. Okay. And here's the sketch of our algorithm. I don't have enough time to show you all the details, but just mention two things. So first, this variational problem, it actually corresponds to the, I used to mention to you the Hodge projection equation shown in theorem 1. So if you can show that the solution of this variational problem, you are minimizing on phi, the solution is exactly the solution to the Hodge projection equation I showed you before. And here, for this functional, we are actually minimizing this functional at every iteration. So this functional is actually kind of like the proximal algorithm or the JKO scheme for solving Wasserstein gradient flows. Okay, so now let me show you some examples. The first example is still about quadratic potential. Because we can get an explicit solution for quadratic potential, it will be useful. So we can directly use the explicit solution to verify our numerical results. So we just choose V like this, and sigma is the kind of diagonal matrix with mu equal with entries 3. And here are some results. So since we are in R4, so we just project every sample points onto the 1-2 plane and the 3-4 plane. And when time evolves, you can see the difference. So after about 100 iterations, the left-hand side, all the points has already converged to the Gaussian distribution centered at 3, with smaller variance. And on the right-hand side, the distribution has it haven't converged, but it's almost there. Finally, it will converge to a Gaussian distribution centered at 3, and it has a non-isotropic shape. And this is actually reflected from our, so this actually agree with the explicit solution of this equation. Okay, and here are the mean trajectories of these two process. So you can compare this two mean trajectory with the exact solution. So in this one, on the 1-2 plane, because the two components are exactly the same, so it is a line segment, and it also has exponential convergence here. And in this case, on the 3-4 plane, the mean is actually, here is e to the negative t, e to the negative 40, so there are some curvature here. So it is also captured by our results. Okay. And finally, let me give an example in R30. So we consider a symmetric potential like this. And to make you feel better with this potential function, I draw the heat map of this function in 2D, look like this. So you can imagine that when t goes to infinity, the distribution will converge to some distribution whose sample points are concentrated on these four corners with highest density here and lowest density here. So let us check the examples. Since we are in R30, there's no possible to visualize the data points, so we project it onto some random planes. So I project them onto the 5th and the 10th plane, and they look like this, the results. So let's move on. So after about 1,000 iterations, finally we are here. So it actually agrees with our expectation. We have the highest density here, lowest density here, and most of the data points concentrate on the four corners. Okay. Finally, let me say something about our undergoing research and the future directions. We are actually working on more examples for high-dimensional Fokker Planck equation, and we are also working on establishing the error analysis. For future directions, as I have shown you, so probably we want to do something on sampling. And also, many kinds of dissipative PDEs have a gradient flow structure. So if our algorithm works, probably we can also apply our algorithm for solving other types of dissipative PDEs. Okay. Yeah, that's all I want to say. Thanks for your attention. Oh, and here are some references I used to mention in my talk. So if you are interested, you can check them.
Okay, thanks for this very nice talk. Do you have some questions?
Can you investigate or would it have a meaning to make some mixtures of your Fokker Planck?
Mixture?
Yes, several ones at the same time. And such that you have several drifts.
Several drifts. You mean which example?
Oh, whatever you find, the last example.
Okay.
I mean, because
This one?
no, even before. You know all the example. So basically, it doesn't sound to me. So there's no meaning.
Oh, which one?
So could you make some mixtures of Fokker Planck? Take several ones and look at several shapes.
Several ones.
But are you maybe referring to the potential being composed of
Yeah,
multiple
several
parts?
potential
Yeah.
and several.
Oh, several
Yeah,
potential.
yeah, just have a more complicated potential.
Oh yeah, actually we are trying to do examples on that, like Rosenblock potential or mixed Gaussians. Yes, we are still working on that.
Oh, we have another question.
In your map, you're assuming that your map T has some nice properties, right? Which assumptions are they, and what consequences do they have on the regularity of your solution?
Oh yeah, actually, so when we are establishing the series, it is necessary to assume T theta is invertible and smooth. But actually, during our numerical experiment, actually those regularity seems not that important. So even though your T theta lose some smoothness, it still works for the numerical examples. Yes.
Generically, it is probably almost always smooth.
Yes.
As far as I understand, normalizing flows are also nice in terms of models because you can actually compute the density of the push forward? Have you tried doing that, or just
Yes, very good. So I use the reason for one of the most important reasons for choosing normalizing flow is the log rho theta, which appears in the entropy term is very easy to compute. You have explicit solution, so that is one of the most important reasons why we choose normalizing flow. Yes.
Okay, it's a great discussion. Thanks a lot again.
Thanks.